Hello.
Hey Wiley.
Hello. Okay. Hi.
Yeah, can you hear me?
Yeah, I can hear you.
Okay, that's good, that's good. Oh yeah, you know how I gave you this problem one time on the whiteboard, like the nucleophilic acid with
Yeah.
alcohol? Someone on TikTok corrected me. I got it wrong. Because you
Because
see,
of benzene?
yeah,
Okay,
the
that's what I thought.
secondary benzylic carbocation is more stable than the tertiary carbocation because it can do resonance. Yeah. Hey, Elysia. How was your break?
It was pretty good. I was all over the place.
You
I
were all over the place. You
Yeah,
traveled.
yeah, I was spending time with family. Um, yeah, out in like Davie City,
Hmm.
Sac area, Richmond area.
Oh my gosh.
Yeah, I got a lot of
You were moving on the go all the time.
yeah.
Huh. That's
How
good.
about
That's good. I went to Vegas for my friend's 21st birthday for 5 days.
uh-huh.
I had a Christmas family party at my house. And then for New Year's, I went hiking with some friends. And then I was so sore after that. And then everything else, I slept a lot, rested a lot, uh, hung out with friends, family, walked my dog a lot. So it was a much needed rest for sure.
That's nice.
Yeah, it's good. But now I'm ready. I'm ready for this quarter. I
Me too. I'm kind of scared.
kind of scared. But Helix 118B, you get to use a note card. Oh yeah, you had a note card with Wave last quarter. I forgot.
Yeah,
I forgot.
yeah, she was unpredictable. A little,
Unpredictable.
just a little bit.
Yeah, I heard her code was pretty good though from last quarter. Like the
Yeah,
curve.
I mean, I passed, so
Mm. Yeah. Hey Peyton, how are you?
Good, how are you?
I'm doing fine. Are you? Wait, I think you wanted to be as well, right? This quarter.
Yeah.
Yeah. How was your studying been going over the break for wanting to be?
It's good. I pretty much finished chapter 12, but I wish I studied more.
Chapter 11 is alkenes. Is chapter 12 alkynes, or is that something else?
I think chapter 11 is just NMR and introduction to alkenes, and 12 is
Uh,
also alkenes.
12 is alkenes. I see. Okay. Makes sense. So let me share my screen. Do you guys have any questions to start off with? If not, I could just go over like some alkene reactions, and for Wiley, I'll go over alcohol and Grignard reagents.
I had a question about an NMR graph, but I can wait till later.
Uh-huh. Yeah, you can send a file on the Zoom. I just turned on that setting, so try it out, and let me see if I can like access that file through the Zoom. And then while you do that, I'll go over Grignard reagents and organometallic for Wiley. So an organometallic reagent is going to be a reagent that has a negatively charged or positively charged carbon atom, right? So you can think of it as a nucleophilic carbon atom. And this reagent will allow us to add carbon carbon bonds to a molecule, right? It allows us to add or extend the carbon chain. So an example of that would be like there's two organometallic reagents that um, you're gonna be exposed to, which is what Grignard reagent for one of them, and another one is going to be an organolithium reagent. So for the Grignard reagent, that is going to have MGBr or MGX, right, attached to an R group. Or X can be usually chlorine or bromine. It could be iodine as well, but the most common thing I've seen is bromine, right? That's the most common atom I've seen for X. right? Whenever you see MgX or like MgBr, the carbon directly attached to the Mg is going to be negatively charged, right? So an example would be something like this. If you have this MgBr here, this carbon atom here directly attached to that magnesium has a negative charge, right? And that is what makes it nucleophilic. And a way that you could think about it is that this carbon here is more electronegative than the magnesium, you could say. And if it's more electronegative than the magnesium, it's going to withdraw electrons from the magnesium, making it more negative charge, and the magnesium more positively charged. This OChem class is 128B, but this was covered in the end of 118A. So this is the end of 118A, beginning of 128B. Right. So for organolithium, it's the exact same thing, but instead of MgBr, you're gonna have lithium, Li. So when you have something like this Li is the partial negative charge. Is my audio okay for everyone? Am I cutting off? Because there's a little bit of lag on my screen.
It cut off a little bit, but I could understand.
I cut off a little bit. Let me go switch to my hotspot
Yeah.
real quick so then it's more smooth.
Okay.
Yeah. Okay. Okay. Hello, hello. Can you guys hear me?
Yeah.
Okay, okay. It should be much better now. Let me know if I still cut off. Okay. Okay. So now these organometallic reagents, they are going to be considered strong nucleophiles and strong base, right? And in OChem, one of the fastest reactions that you could have is an acid base reaction, right? So when it has the chance to either act as a nucleophile or a base, it's going to choose to act as a base instead of a nucleophile, because acid-base reactions are faster than nucleophile electrophile reactions. So when there's an acidic hydrogen present, then the organometallic is going to deprotonate that acid instead of attacking a electrophile, right? So let's say we have this Grignard reagent here, and I'm gonna react it with 4 things. Let's say 4 things, right? Actually, I'm gonna do 5 things because you might see this 5th thing later on. So let's do 6. And CO2, acid workup. And all of these here will have an acid workup step to clean up the reaction and make it neutral. Let's actually not do acid workup for these two, just to emphasize a point. So for the first reaction here, we actually don't need the acid workup step because this is just going to be SN2 reaction. We have our nucleophilic carbon here. What do you think is going to happen between this reactant molecule and this reagent here? Right? What is going to happen between them?
Is it going to attack the polar bond?
Yeah, it's going to attack the positively charged carbon, right?
Oh,
So
yeah.
this is the polar bond, where this is the positively charged carbon. This is the negatively charged bromine. This negative charge is going to attack that electrophilic carbon, kick out the bromine, SN2 reaction. So this first reaction is SN2. And the reason why I'm starring this and dotting this is because that's the technique I use when I combine the 2 reagents together to avoid adding a carbon or losing a carbon, right? So that's the star carbon. This is the dot carbon right here. The MGBR, it dissolves away in the solution. It just disappears when this reaction happens. It dissolves into ions, right? So this right here would be the new bond between the star and dot carbon. The new bond that is formed from this attack, and this dot carbon here is attached to a methyl group like that, which is this methyl group here. The bromine gets kicked out as a Br minus like that, right? Any questions on that one?
No.
Okay, so for the next one, what do you think is going to happen between this Grignard reagent and this set of reagents here?
Is it going to attack the electrophilic carbon, double bonded O? The carbon?
The electrophilic carbon, yes, it will attack the electrophilic carbon, and that's going to break the octet rule, right? Because this carbon already has 4 bonds. So to conserve the octet rule, we have to
With the double bond to O.
Yeah, move the double bond onto the O to give that O a negative charge. So when we visualize that, this is the star carbon. MGBR dissolves away in the solution. That's the new bond between the star carbon and the dot carbon, right? This dot carbon here is this dot carbon of the aldehyde, which is attached to a methyl group, single bond O minus now, and a hydrogen, but I'm going to leave that hydrogen out as invisible, like that, right? So now that's the end of the first step, which is why I bring in a second step of acid workup to clean up this O minus alkoxide ion, right? Reprotonate that O minus to become neutral OH, right? So it's going to be the same thing for the third set of reagents, but instead of an aldehyde, we have a ketone where this is the star carbon. This is the new bond between the star and dot carbon. This dot carbon here is attached to 2 methyl groups, let's say like this, 1, 2, and a single bond O minus, which will eventually become protonated to become neutral OH, like that. So same exact mechanism as the last reaction, but instead of having a secondary alcohol being formed, we have a tertiary alcohol being formed because of the extra R group of the ketone right there, right? We don't have a hydrogen, we have an extra R group from that ketone. Okay. Now, these next 2 reagents here is going to talk about the basicity of this Grignard reagent. So far, what we've done is we looked at the nucleophilicity of this reagent, right? This Grignard reagent acts as a nucleophile that attacked these electrophiles to form this product. But now we see that we have an acidic hydrogen in the carboxylic acid here. So what's going to happen is that we are going to deprotonate that carboxylic acid to get this carboxylate O minus, and the side product, or you could think of this as main product as well, would just be this R group of the Grignard reagent, right? Because before, this star carbon here has 2 hydrogens, but now this star carbon has 3 hydrogens, 1, 2, 3. It gained a hydrogen from this carboxylic acid right here, right? So this is just an acid-base reaction where the base is this Grignard reagent and the acid is this carboxylate right here.
Wait, so how would you draw the mech for that?
Yeah, so the mech for this would look like this, where if this is the base, this base is going to grab that hydrogen. The bond between the hydrogen being grabbed and that oxygen right there, those 2 electrons are going to pop onto that oxygen, giving that oxygen a negative charge, like that.
Would you have to draw anything for the MGBR when it attacks the...
No, MGBR, it just dissolves away in the solution. Like for the rest of these other mechanisms, we don't draw any arrow from the MGBR. We draw the arrow from the carbon directly attached to the MGBR. Right, and we just assume the MGBR dissolves into ions like Mg2 plus and Br minus ions, but we don't include that in the product. Right.
Okay.
Okay. So now, this would be important because if you look at this next reagent here, there is an acidic hydrogen, which is the alcohol hydrogen, because it is partial positive charge attached to that electronegative oxygen, and there is an electrophilic carbon, which is the carbon of carbon here. So there's a competition now between the acidic hydrogen and the electrophilic carbon fighting for the Grignard reagent's attention, right? So like we said earlier, acid-base reactions are one of the fastest reactions you see. So if that's the case, what do you think is going to happen here?
It's going to deprotonate.
Yeah, it's going to deprotonate the alcohol hydrogen by grabbing it, that bond between the hydrogen being grabbed and the oxygen, is going to pop onto the oxygen, giving that oxygen a negative charge. It's not going to attack the ketone, right? It's not going to attack this carbonyl carbon of the ketone because acid-base reaction happens faster than that reaction, the nucleophile electrophile reaction. Right? Okay. So now for this last one here, you probably see this later on, but if I were to draw out the Lewis structure of carbon dioxide, which is that CO2 right there, what do you think is going to happen between this green reagent and the CO2?
Um, wait, would it even do anything?
It would, because we have a negative charged carbon here. Do you see any electrophilic atoms in the CO2? Any positively charged atom?
Say the carbon.
Yeah, the carbon is the positively charged atom, so that's the electrophile. So what's going to happen is that this dark carbon is going to attack the electrophile. That's going to break the octet rule. So we have to pop one of the double bonds onto the oxygen to give us this intermediate here. This is the starred carbon. This is the dot carbon. This is the new bond between the star and dot carbon. That dot carbon is attached to a double bond O and one single bond O minus now, right? Because this single bond O minus came from this double bond being popped onto the oxygen right there. Right.
Hmm.
Now, once we have this O minus, we can just clean it up, make it neutral by bringing in the second step of acid breakup to give us this neutral carboxylic acid right there.
Let's see.
Right. So this reaction added a carboxylic acid to the molecule, right? And it extended the carbon chain by one carbon. Before it was 1, 2, 3, 4 carbons long, but the molecule is now 1, 2, 3, 4, 5 carbons long, where that extra carbon that was added is the carbon of the carboxylic acid. And you see this at the end of the quarter when you talk about carboxylic acids and their derivatives, right? But I
Okay.
want to just
Yeah.
introduce it to you now, so then you're ready for that, right?
Right.
Okay. So now let me give you some practice problems to try out, and then I'll move on to that NMR problem that Peyton sent, and I'll come back I'll come back later to check your answer, right? So let's do this. Yeah, two more. Okay, last one. Okay. Try out these 5 problems, and then I'll check this at the end. Let me know when you have a screenshot of this, so then I can move on to the NMR problem.
I got it.
Okay, okay. Let's see here. Oh, what the heck? Let's see. Let me see. Let me see. Hmm. Let me see. Hmm. Okay. Does Helix have different like times of the lecture for different sections, or is everyone taking the same class at the same time, the same frequency?
I think there's 2 sections.
Uh-huh. I see, I see.
If the file doesn't work, I can try to send like a screenshot.
Yeah, I think the file. I think I'm getting it right now. Okay, okay. Yeah, I think it would work. It would work here. Let's see. Just gotta wait for that email. Okay, here it is. Okay. NMR. Um, was there a specific problem you wanted to go over, or did you want to go over like some of these and it's in the thought process of
Just practice 1.
practice one? Okay, okay. So for practice 1 right here, you first did the DOU, which is the first step. That's good. 5, uh, which is 2. Wait. Is it 2c plus 2 minus h minus x plus n all the way to, which is 18 plus 2 minus 10. 2, that's minus 10. Yeah, it's 5. Okay. And you have a good guess that this is most likely going to be a benzene ring, because if you have a DOU of at least 4 or more, then that is going to most likely have a benzene ring, right? Because this benzene ring here has 3 double bonds and 1 ring, making 4 DOU. And to check that, we could check between 6 to 9, right? 6 to 9 ppm on the HNMR, because these benzene hydrogens here will show up between 6 to 9. And we do see peaks around 6 to 9, so that confirms our benzene yes, right? And now, after that, we have to look at how many substituents does that benzene have, right? Is it unsubstituted? Is it monosubstituted? Is it disubstituted, trisubstituted, so on and so forth? So because we see 2, 3, 5 hydrogens in this benzene region right here, that means that our benzene is monosubstituted, right? Because the benzene here has 6 positions for 6 benzene hydrogens, but because we have 5 benzene hydrogens in the benzene region, those 5 benzene hydrogens are going to be here, meaning that we have 1 substituent, 1 random R group, I don't know what that is yet, on that benzene ring. So that's how many substituents are in that benzene ring. It is monosubstituted because we have 5 benzene rings there, benzene hydrogens there. But if you see 4 hydrogens, that would mean that this benzene is disubstituted, and then that's when we talk about ortho, meta, para, relationships, which I will go over that after this problem, right? So now we know that our benzene is monosubstituted. Then we have to look at these other peaks right here. Let's look at this peak right here, the 2 hydrogens with 1, 2, 3, 4 subpeaks. So back in 118A, do you remember how many neighbors these 2 hydrogens would have if it has 4 subpeaks?
If we're doing 3J coupling, it will have 3 neighbors?
Yes, 3 neighbors, because the number of neighbors would be equal to the subpeaks minus 1. Right? We have 4 subpeaks minus 1. That is going to be 3 neighbors. Right? Think of this as the n+1 rule is equal to this number of subpeaks. Right? 3 plus 1 is 4, which is why we have 4 subpeaks here. Okay, that's good. So these 2 hydrogens here is going to have 3 neighbors. 3 neighbors. So now let's look at where it is located on the HNMR. We see that it is around 4.25, 4.3-ish, which would make it de-shielded, more de-shielded. So if that's the case, what does that mean? What does that mean when those 2 hydrogens are de-shielded?
They're near more electronegative atoms?
Yeah, they are more near electronegative atoms or electron withdrawing groups. And if we look back at our chemical formula here, our most electronegative atom is alkene, right? So when I draw out the fragment here, I'm going to draw out these 2 hydrogens like that. And this is the carbon that those 2 hydrogens are on. And I'm going to put an oxygen right there, right? Because these 2 hydrogens are de-shielded, meaning that they are near that electronegative atom, like that, right? So now it's 3 neighbors. In order for these 2 hydrogens to have 3 neighbors, what do you think could have been attached to this carbon here to allow for those 2 hydrogens to have 3 neighbors?
I think from the IR we see like CO double bonds, but I'm
Yes, we do have a CO double bond here at the IR 1700-ish region. That is going to be somewhere in the product or the molecule, but we want these 2 hydrogens here to have 3 neighbors. So in order for these 2 hydrogens to have 3 neighbors, we have to add a methyl group here. Right.
yeah.
The reason why we need to add that methyl group there is because that methyl group has 3 hydrogens, which are the 3 neighbors of these 2 hydrogens right here. Right. But to confirm that, how many neighbors do these 3 hydrogens have right here in the molecule that we just formed?
2 neighbors?
Yeah, 2 neighbors, which is going to be represented by how many subpeaks on the HNMR?
1?
So think of it as the n+1
Oh,
rule.
yeah, 3.
3 subpeaks, right? So these 3 hydrogens here is this peak right here with 3 hydrogens and 3 subpeaks because it has 2 neighbors, right? And it is not as de-shielded as this peak is because it is farther away than this oxygen right here,
I see.
right? So now once we have that, let's now count how many carbons we used up. We used up 1, 2, 3, 4, 5, 6 carbons from the benzene, 7, 8 carbons from this group we have right here. So that means we have 1 carbon left, and that 1 carbon left is most likely going to be that carbonyl carbon right there. Where do you think we could add that carbonyl carbon in the fragments we have so far? Right? This, like, think of the 2 oxygens here. 1 oxygen is from this fragment. The other oxygen is going to be from that carbonyl carbon. Where do you think we could attach this carbon double bond oxygen to?
I was thinking maybe like the benzene attachment group.
That is a good thing. We could add a carbonyl like that. So let's do that. right? And that's gonna have that fragment right there. So now we have our two fragments where we can piece these two fragments together like Legos to give us this final molecule here. This benzene, that group, this oxygen here, and that right there. Do you remember what functional group this is specifically? This one right here, not the benzene ring, but that thing circled.
Um, is that an aldehyde? Wait, no, is that a... I forgot.
Uh-huh.
I
Yeah,
forgot the name.
yeah, starts with the E. It sounds like very similar, like to another name. The name that is similar to is ether. But what is the name that's similar to ether?
Oh, ester.
Ester, yes. This is an ester where we have a carbonyl, carbon double bond oxygen, attached to an OR group. That's the ester right there. Right. So this is what I have so far. Let's double check with everything. The molecular formula is C9H10O2. So let's see if we have 9 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9 hydrogens. Let's see if we have 10 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. That's good. We have 2 oxygens. That's good. Now, for the DOU, we calculated 5. So we also have 5 DOU, 4 from the benzene ring, 1 from the carbonyl, 5 DOU total. Right. And everything else would make sense because the 3 hydrogens here is this peak, the 2 hydrogens here is this peak, and then the 5 benzene hydrogens are these peaks right here. And I'm going to explain these benzene hydrogens more specifically by color coding it. Let's say that's hydrogen there, that's hydrogen there, that's a hydrogen here, that's a hydrogen here, and this is a hydrogen here. So there is a plane of symmetry in this molecule, which is down that middle right there. Right now, it doesn't look like it because like the left side has this group, but remember that this is a single bond that can do free rotation. And because it can do free rotation, this OR group here can rotate and it could go onto this other side as well. So the plane of symmetry is down that middle right there. Right. And because of that plane of symmetry, these 2 hydrogens here are equivalent, these 2 hydrogens here are equivalent, and this 1 hydrogen here is unique. Like there's no other hydrogens like that. Right. So that would be represented by these peaks right here. Right. 2, 2, 1. Any questions on how I got this molecule from the first practice problem?
Would you be able to locate which of the two it is? Because it's super blurry from the PDF.
Oh yeah, for this one right here, like the subpeaks, don't worry about it too much. Just look at the thing. Like, don't worry about that. But you do need to worry about that for ortho meta para positions, right? But for monosubstituted ones, you don't have to worry about that, right?
Oh, I see. Okay.
Yeah. Right. And if I want to color code it more, these 3 hydrogens here at the methyl group are going to be those 3 hydrogens, and these 2 hydrogens here are going to be these 2 hydrogens right there. Color coding everything, right? Okay. So what I want to go over is the ortho meta para position for di-substituted benzene rings, right? So you would need to know this to solve the synthesis problems that they give you at the beginning, but you will not learn this until after the alkyne stuff and benzene stuff, which is like midterm 2 material. This is midterm 2 material for helix, right? So this is when we have a di-substituted benzene, meaning that our benzene will have 2 substituents attached to it, right? But there's 3 ways that the benzene could be di-substituted, right? One way could be like this, where the 2 substituents are adjacent to each other. Another way could be like this, where the 2 substituents are 1 carbon away from each other. And another way is like this, where the 2 substituents are anti to each other. are 180 degrees apart from each other, 2 carbons away from each other, like that. So these are the 3 different ways that a benzene can be disubstituted. If the 2 substituents are adjacent to each other, this is what we call ortho. If the 2 substituents are 2 carbons away from each other, that's what we call meta. They're meta to each other, or they have a meta relationship, right? If the 2 substituents are anti to each other, they are para to each other, parallel to each other, right? So some tricks that you might think is like parallel to each other for para, and for meta, M, you could kind of see the M here if you trace out the substituents like that, right? It's like a M right there. And ortho, it's like orthogonal. I don't know, orthogonal. So they like it's just like the closest one possible for ortho, right? But these are just like relationship terms that you have to be familiar with. Ortho is the closest. Meta is like 1 carbon away, and then the para is the farthest away, like that. Right. Okay. So now let's look at the H NMR spectrum for all of these relationships, and see the hydrogen's positions and their number of neighbors, and how many unique hydrogens are there. Right. So for the ortho scenario, how many unique hydrogens would you say there are in this benzene?
I think is it not dependent on the substituents? Because if they're the same, then there'll be 2.
Yeah, if there's a plane of symmetry, then you can have equivalent or symmetrical hydrogens that will count as one set. So let's first see if there is a plane of symmetry in this benzene. Do you see any plane of symmetry that we could draw like a line through to see if there's a plane of symmetry?
I think there is if the 2 substituents are the same. Or is it not? Does it not count if it's in the middle? If you like cut through a double one?
Right, like down this middle right here, or
Oh wait, you can't cut through a double one, right? Oh yeah, yeah.
right. The plane of symmetry here would be down this line right here, because everything on this side of the line is the same thing as everything on that side of the line. Does that make sense?
Yeah.
Right. So because there's a plane of symmetry there, these 2 hydrogens here are equivalent to each other. Right, because they have the same chemical environment. They experience the same surroundings. You could think of it like that, right? They have the same surroundings. If you like live in this hydrogen house, then everything else is like identical as if you were to live in this hydrogen house, right? Like the surrounding environment is identical, symmetrical, right? Another set of hydrogens would be these 2 hydrogens right there, right? Wait. Okay. So this gets into a deeper thing when this would only be possible if the 2 substituents are the same thing, right? If the 2 R groups here are the same. So let's say this was an ethyl group and this was an ethyl group, then that would be the case, right? But in most cases, which you will probably get in the problems, the R groups here are not equivalent. They're not the same. So if this R group here is an ethyl group and this R group here is an isopropyl group, there's no more plane of symmetry, right? Because if you try to make a line through here, this side is not the same as this side anymore. So there's no more plane of symmetry, right? And because of that, all of these hydrogens here are unique. There's no symmetrical hydrogens like that, right? So in the ortho case, we have 4 unique hydrogens like that. Does that make sense so far?
Yeah.
Right. So now let's look at each one's subpeaks one by one. Let's look at the red hydrogen. How many subpeaks would you expect for the red hydrogen?
Would you take into account geminal and vicinal coupling?
Geminal and vicinal, that is going to um, be more for alkene relationships, but for this one here, we'll still be thinking about the number of neighbors on how we calculated the neighbors in 1:A. So if you were to calculate the number of neighbors for this red hydrogen here, you start from the hydrogen and you go 3 bonds away. If it lands on a hydrogen, that counts as a neighbor, right? So
so you have one.
yeah, one neighbor, which is this green hydrogen here. But that is not equal to the number of subpeaks because we have to do the n+1 rule. So if we do the n+1 rule, what would the red hydrogen peak look like here? How many subpeaks would it have?
It will be a doublet.
Yeah, a doublet like this. So that's the 1H right there. Let's do it for the green hydrogen now. What would the green hydrogen peak look like on the HNMR?
A triplet.
Yep, a triplet because it has 2 neighbors. 2 plus 1 is 3. So it's a triplet. Purple hydrogen?
2. Oh, wait, 3 pieces. So
3 subpeaks as well because it has 2 neighbors. And then the pink hydrogen would be the same as the red hydrogen. It has 1 neighbor, so it will be a doublet, right? So when you see this specific pattern on the 6 to 9 ppm range on the HNMR, right, where you have 4 benzene hydrogens total, 4 different unique peaks, 2 of them are doublets, 2 of them are triplets, that's how you know your benzene is exactly ortho, right? Your di-substituted benzene is exactly ortho. The 2 substituents are ortho to each other. This is what you use to determine if your di-substituted benzene is ortho, meta, or para, right? This is the tool that you're going to use here. Okay, so let's move on to the meta position or meta scenario. How many unique hydrogens do you see in this benzene if the R groups here are different from each other? Like let's say this is isopropyl and this is ethyl here. They're different from each other. No planar symmetry in that case. How many unique hydrogens would you expect?
also 4.
Also 4, that's right. So let me color code them and let's do the same thing. For the red hydrogen, how many subpeaks would you expect for the red hydrogen?
It will be a singlet.
Yep, it would be a singlet, right? And that's the most distinguishable feature for the meta disubstituted benzene ring, right? If you see a singlet there, then you most likely have a meta benzene. What about for the green one?
Doublet.
Yep, doublet, purple.
Triplet.
Yep, and then pink.
Doublet.
Yep, doublet as well, right? So when you have 4 benzene hydrogens, 6 to 9, but you see 1 singlet, you could almost automatically say that this is a meta ring, right? So now for para scenario, how many unique hydrogens would you expect for the para scenario?
If the 2, wait, if the substituents are different, but they can.
Like
Oh
if
yeah,
this,
so 2.
yeah, because like you know how before we said there were 4 unique hydrogens for ortho and meta. Even though for para the 2 substituents are different, there's still planar symmetry down this middle right here.
Yeah, I see.
Right? So that means there's 2 unique sets of hydrogens, which are going to be these 2 hydrogens here. They're one set, and these 2 hydrogens here. That's another set right there. Right. So now our integration would be 2 for 2 peaks. How many subpeaks would you expect for this red hydrogen to have right here? Just look at this one red hydrogen right here.
A doublet.
Yep, a doublet because that's 1 neighbor. But instead of writing 1H, I'm writing 2H because there's 2 hydrogens for this peak right there.
I see.
Right, and that would be the same for the green peak, a doublet for 2 H's. So when you see 2 doublets with 2 H's, that's para benzene between 6 to 9.
That app is so smart. It's gonna be so helpful for that.
Yes. I'm glad. Like this tool would be so helpful for you to solve these types of problems here. Looking at this now, what benzene would you expect? What kind of benzene?
So para.
Yeah, para. This benzene here is gonna be para, and you're gonna see that when you solve that, when you go work through this.
That's good. Thank you.
Yeah, no problem. Okay. So, Elysia, did you have any alkene problems that you had, or you want me to teach you alkene reaction?
Yeah, I could do alkene reactions.
Alkene reactions? Okay, okay. Let's do that. Let me start off. Have you learned about heat of hydrogenation yet?
Um, I went over it by myself,
Mm-hmm.
but not in lecture yet.
Not in lecture yet? Okay. Uh, what section did you end up reviewing up until by yourself? Like what do you remember?
Ooh, I think the last thing I did was acid catalyzed equilibration of alkenes.
Acid and would the reagents be like acid and water or acid and alcohol for alkene?
Yeah, it was kind of like going from a cis to a trans formation with a catalytic H plus.
Oh, that reaction. Okay,
Yeah.
okay, that's like isomerization or acid equilibration, something like that. Yeah. Okay, yeah. That's good. Um, uh, if I were to give you this list of alkenes right here, in what order would the alkene stability increase?
Um, from left to right.
Mm-hmm. That's good. That's good. Stability increase from left to right because the more substituted the alkene is, the more stable it is. They give it like the carbocation one.
Yeah, the more friends.
Right. Mm-hmm. This here is unsubstituted because there's no R groups attached to it. Hydrogens do not count as a group, right? They're too small, too tiny. This is mono substituted. These three are di substituted. This is tri substituted. This is tetra substituted, right? But looking more specifically into the di substituted ones, this is geminal, this is cis, and this is trans, right? Geminal meaning that the two R groups are on the same carbon. Cis meaning that the two R groups are on the same side but on opposite carbons. Trans meaning that the two R groups are on the opposite side, right? Opposite side, on different carbons like that. So if we talk about stability arrows, the arrows would be like this, right? Increasing in stability. Except for geminal and cis alkenes are relatively similar in stability, right? And the reason why the trans alkene is more stable than the cis or geminal alkene, can you think of a factor that would make that trans alkene more stable? Think back to 118A. Like what factor do you think would make the trans alkene more stable?
It wouldn't that be with intermolecular forces?
Intermolecular forces or something close to that. Think about the R groups and its physical space. Like if they are gonna bump into each other or not.
They won't bump with each
Uh-huh.
other because they're on opposite sides.
Right. Whereas the cis and geminal alkenes, they will bump into each other, which increases steric hindrance. And steric hindrance is bad. We don't want that, right? That decreases the stability.
Right.
Right. Trans here does not have steric hindrance because they are opposite sides of each other. Okay. So that's good. And we already know about carbocation stability. And the equilibrium that you talked about, turning from a cis to a trans alkene, is going to be something like this. Let's say we have, like, let's start off simple. This cis alkene, and we put some kind of acid to it, like sulfuric acid, H2SO4, and we isomerize it into the trans alkene. When you think of an alkene, think of it as nucleophilic or basic, right? Because can you tell me how I can get a resonance structure from this alkene right here? Like what arrow would I have to draw to get a resonance structure of this alkene right here?
Um,
Right. The resonance structure that I draw here is going to be like less stable than the one I have right here.
right. So I
How
guess
many? Uh-huh.
either left or right side.
Yep. Like the bond here of the alkene has two electrons. We could put it on the right or left side. Doesn't matter because um, it's symmetrical and the carbocation would be stable on either side, right? So when we do that, we are going to have a negative charge on that side that I just put it on. And because this carbon here lost the bond, that carbon would have a positive charge like that, right? In this case, it was simple to choose which side it would go on because the carbocation would be stable on either side. But let's say we had a tri-substituted one, then it would matter where the negative charge goes to because we want to form the more stable carbocation.
Yeah, so you would move it to the more substituted?
The electrons to the more substituted or the carbocation to the more substituted?
Well, I know you want your carbocation to be in the more substituted.
Right.
So that's like a factor you have to consider, but like when you're doing the reaction, you want to attack from the I think you want to attack from the less substituted.
Yes, we want to attack on the less substituted side because we want the carbocation to be on the more substituted side, right? Because of that, when we do the resin structure here, I want to move the electrons to the less subside, not the more subside, right? Because I want the more subside here to lose electrons for us to have that more stable, more substituted carbocation.
Right. And that's like very important to consider, like with the reactions.
That's correct. It's very important to consider to see which carbon of the alkene attacks an electrophile or nucleophile, which is the less subcarbon right here. We see that negative charge on the less subcarbon right there, right?
Right.
So that's going to be very important for other reactions that we go over. But for now, in this case, it doesn't matter because they're symmetrical. Both carbons are equally substituted, right? But the reason why I'm telling you to draw the resin structure here is to show why alkenes can act as a nucleophile or electrophile. It's because they have this bond right here, which has 2 electrons, and those 2 electrons can be used on one of the carbons of the alkene to attack an electrophile or some sort of acid. Right.
Right.
So now, when we have a strong acid here, we are going to protonate the alkene, one of the carbons of the alkene. In this case, it doesn't matter, like we said, because they're equally substituted. I'm going to draw the arrow from this carbon, grabbing that hydrogen. This bond between the hydrogen being grabbed and oxygen is going to pop onto the oxygen right there to give me this intermediate right here. Right. I'm just going to draw out the hydrogen here and circle it pink to show that that pink hydrogen is now attached to this carbon that attacked it. Right. And then HSO4 minus leaves as a conjugate base like that. And this carbon here that lost the bond, right? Before it had 4 bonds, 1, 2, 3, 4, but now it only has 3 bonds, 1, 2, 3. And because of that, it has a positive 1 charge now, carbocation there. Right. And back in 1A, do you remember what kind of step we have to look out for whenever we form a carbocation intermediate?
Is it to check if it's in its like favorable spot?
Yep, most favorable spot. And if it's not, what is that step called when we shift it to the more favorable spot? There's
Hydrogen shift.
Yeah, hydrogen shift. Yeah,
Yeah.
you got it. Hydrogen shift, or if there's no hydrogen, you can do an alkyl shift, like a methyl shift. But most commonly, hydrogen shift. Right.
Okay.
So now, because of that, positive charge right here. This is a single bond that can do free rotation now, right? Before, we cannot rotate that double bond to the trans alkene because double bonds have no free rotation, right? Because of their 2 like parallel p orbitals there, we don't want to break that p orbital, so that's why it has no free rotation. But this single bond here, sigma bond there, can do free rotation. So when we rotate it, we can rotate it like this, right? Where we just like swap the methyl and hydrogen spot like that.
Right. And then are they like picky on if we draw in like the wedged in the like dash position? Because I know like that might also.
Oh, right. The wedge and dash position. Yes. So if this was a dash right here, and we flipped it up, this would be a wedge now. If we flipped it up there, like if this was a dash bond, and we flipped these 2 together, then the stereochemistry would also flip like that.
Okay, that makes sense.
Right. But that won't matter in the end product because what would happen next after we get this form.
We would have the OSO3H come back in.
Uh-huh.
And
the way that I'm drawing it here is like if it makes more sense for you, then you could use it, but it might make more sense if you see as HSO4 minus like that. That's the way that you're probably going to see it. The reason why I'm doing it in this form is because I want to show accurately where the negative charge is at, like which is on this oxygen atom right here.
okay, so then it would use its electrons to grab the hydrogen, and then it would
yes. Which hydrogen would we grab? That's good.
In this case, is it the one the one like below?
This one right here?
Yeah, I think so.
If we grab that hydrogen right there, the bond between this hydrogen and carbon is going to make a double bond right there, giving us this double bond right here.
Which we don't want.
We don't want that, right? We want to go for the more substituted hydrogen to get the more substituted alkene.
Right. So the other one.
Yeah, this one. Grab that hydrogen, make a double bond there, get to the final product there.
Ooh.
Right. So this is E1, right? Once we have the carbocation and we do E1, we make the alkene right there. Right.
Ooh. Okay.
Yeah. So like SN1, SN2, E1, E2, those reactions, they are gonna like show up in future reactions you learn, like just like this one, right? This is an E1 type mechanism. Once we have the carbocation, we eliminate this hydrogen to form this double bond right here, just like what we did in E1.
That's cool.
Yeah.
Well, like mechanisms that we learned in A comes back like quite often, like you.
Grignard reagents, like that is very important.
Okay.
E2, right? In E1 elimination, especially for alkenes, because that's how we form alkenes. Like one of the ways we form alkenes.
Okay.
SN2 for sure is always going to come back. Like all the SN2, SN1, E1, E2 reactions will come back. Grignard reagents. Ethers, not so much, right? Ethers is more of a 118A thing, and it doesn't really come back in 118B or C.
So like not ether epoxide.
Epoxides, ethers, yeah, they're more for 118A, but depending on your professor, they might want to bring it back. Like Helix, he tends to bring back epoxide sometimes, but not as much. It's rare for Helix, but Nisiri is common.
Okay.
So not as high yield, the ether and epoxide stuff, as the E2, E1, Grignard reagent, SN2, SN1. Free radical halogenation, like that's more 118A. Yeah. The most important ones I would say is the SN2, SN1, E1, E2, and Grignard reagents for 118A. That builds onto 118B and C.
Okay, yeah, because I was a little bit nervous about like how much do I have to like, I guess like refresh.
Right. Not so much, because 118A is like more of the foundational concepts like resonance, acid base, drawing molecules or in bond line form, nomenclature, mechanism, like the arrows, what they mean. Like that is just like getting you used to the language. And what is in B and C, that's when you start like the real OChem. What is in A is still OChem, like the foundation OChem, but you're gonna start learning more reactions, mechanism, synthesis, spectroscopy, heavy in what is in B and C. Right? What is in A was just to teach you the language of OChem, basically.
Okay.
But the end of one in A was getting real. Like when you learn about SN2, SN1, EU2, alcohol reactions, Grignard reagents. That's like a sneak peek of what you're gonna see in one in B and C.
Okay. Would you say that 118B is like the hardest out of the three? Because I hear that a lot.
One is in B.
Yeah.
That's what most people think, because they are not used to studying for like the reactions. Like there's gonna be a lot of reactions thrown at you and mechanisms and synthesis, and they don't know how to like organize the reactions, categorize them in a way that makes them like more streamlined. And because like a lot of reactions are gonna be very similar to each other, right? And then a lot of students, they try to memorize each reaction one at a time. It's instead of understanding the bigger picture of like how how they are related to each other, right? They just like focus on one at a time instead of thinking about the big picture, how they're related, and organize them that way. Um, for me, I took 118 A and B in COVID, like online. So it was like easier than 118 C for me because 118 C was the first quarter back in person, fall 2021, and that was when I like struggled the most in 118 C. Right.
Okay. Yeah.
Uh-huh.
Okay, that makes sense.
Yeah. Right. And also, people also say 118 B is the hardest is because in 118 C, they like learn how to study for like these reactions now. But if you come to these office hours, I would like teach you tips and tricks on what to study for, what to look for to save you like time and like not be as overwhelmed, when you see these reactions coming at you. Yeah.
Right. Okay. Thank you.
Yeah. Mm-hmm. Okay. Wiley, were you able to finish the 5 Grignard reagents?
Yeah, I
Organometallic columns?
think I got all
Uh-huh.
of them right.
Okay. Let's see. Let's see it. You can send a screenshot here on Zoom for me to check, or you could just explain to me, like through
Uh,
words. Uh-huh.
I drew, okay, for the first one, I drew all the carbons, uh, like
Okay.
the original carbons.
Yep.
And then where the MGBR used to be in that position, I drew like a carbon line, like another carbon, and then attached to that is an OH, an H, and then the benzene ring.
You got it. That's correct.
Oh, I
Nice.
got it.
Yep. You got it.
Okay.
This is a
Uh,
new bond. I'm leaving the H as invisible, but that's good. You got
yeah.
it. Uh-huh.
Se the second one should be a ketone and an acid workup, I think.
Yes, a ketone. So I'm going to draw the carbonyl here. Second step is an acid workup. What are the 2 orbitals of the ketone?
It's just I just drew a regular ketone like carbon, carbon, carbon. That
Like
work.
this.
Yeah. Uh,
So if we have this right here, let me store this carbon, which is this star carbon. Let me dot this carbon, which is this dot carbon, making this the new carbon. When we look at the dot carbon here, this alcohol is the carbonyl oxygen.
oh wait.
What R groups are attached
Oh,
to this
I just wrote it down wrong. Oh,
dot carbon? Uh-huh.
there's supposed to be extra carbons. There's an extra carbon, right? On the
On one of them, right?
yeah, okay.
Because
Oops.
we have an ethyl group, which is this ethyl group, and a methyl
Yeah,
group, which is that methyl group. Right.
okay. I
That's good.
just wrote the product wrong when you
Mm-hmm.
copied it.
Oh, I see. Yeah. Like, did you draw this product like that right there, but without the ethyl group? Yeah. Like, did you draw like 2 methyl groups like that, like in
Yeah, no,
dimethyl?
I just retrieved my
I
groups.
see. Yeah. That's good. That's
Yeah,
good.
okay.
Uh-huh.
Okay, the third one, I'm not sure.
Uh-huh.
So I just
Uh,
drew like the 3 ethyls connected together,
uh-huh. Right.
and then attached to that is or like a double bond O,
Uh-huh.
and then I just put like a BR.
Oh, BR over here.
Yeah, but I was kind of confused, like
Okay.
how
So
yeah.
this one here, that's gonna be the end of the quarter. It's not gonna do this reaction, right? So because this is gonna add 2 times if this was a BR. Instead of a BR, let's look at this dot carbon here, the carbonyl carbon. This is dot carbon, this is a star carbon. This is the new bond between the star and dot carbon. What is attached to this dot carbon do you see right now? We have this alcohol, which is this carbonyl, this triethyl group, which is this triethyl group, and what else is attached to that carbon, that dot carbon? It's invisible right now.
Iron?
Hydrogen. So what we have to draw here is a hydrogen.
Wait, is that it?
That's it.
Oh, wait, can you draw it like the mech?
Yeah,
Like,
let me draw the mech. So this is the star carbon. Attack the dot carbon, pop the double bond onto the oxygen. When we do that, this is the dot carbon. That double bond O is now a single bond O minus. This is the new bond between the star and dot carbon. That star carbon is attached to the cyclopentane group. And the MGBR just dissolves away in a solution. And then we acid work up the O minus to OH with the acid workup step.
oh, okay, I see.
Okay. This hydrogen here is still there. I'm just leaving it as invisible.
Okay.
Right. So that BR that you added right there, it will do something else. We'll get back to that at the end of the quarter. Right?
Oh, it did. Oh, oops.
Yeah. The BR here, it would actually add this R group 2 times, like that. If you added that BR there.
Oh, okay.
Uh-huh. Right.
Hmm.
Okay. Next one.
Uh, I drew the original carbon branch.
Mm-hmm.
Wait, yeah, and then the bottom OH is like that branch is intact,
Mm-hmm.
and then on the from the right, the second
Mm-hmm.
rightmost carbon on the five carbon chain, I
Yep.
drew a ketone.
Uh-huh. Ketone. Like that.
Or yeah, a carbon, yeah, and then I just put the really long branch with the Li at the
Like this
very
right
right.
here
No, the one on top.
on top.
Yeah,
Oh, so is this still a ketone or
yeah, so yeah,
and you put a really long branch like this
yeah, with the
uh,
Li.
on
Bottom
this
of it,
carbon?
right.
Oh, okay, okay, yeah, yeah. So for this one right here, we have a Grignard, I mean not Grignard, organolithium reagent, which is this RLI. And we have two competing things for that organometallic. This electrophilic carbonocarbon or this acidic hydrogen.
Oh wait, oh my gosh.
What is gonna
I
get?
put two OHs for the reactants. I was like, which one will deprotonate first? Oh, never mind.
Oh, no, 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 no. There's no two H's, one OH. Uh-huh.
Oh,
Yeah. And even if there were two OHs, an R group would not attach onto the molecule, right? Because we can't attach an R group to OH. We can only attach it if it's a carbonyl or
okay.
haloalkane, right? Unless you were talking about like that as a side product. Because the first step here is that this is going to get deprotonated to get a negative charge. And then that negative charge is just going to get protonated by the acid breakup to get the OH. And then we have a 1, 2, 3, 4, 5, 6 carbon chain, which is this two,
Yeah.
three, four, five, six carbon chain like that. Like that's the side product.
Oh, it is. Oh, okay. Wait,
Or
why
you
doesn't
can
that?
think of it as a major organic product as well. These are the two major organic products.
Wait, why doesn't that add to the thing?
Yeah, it doesn't add to the thing because when this Grignard reagent here attacks the hydrogen, right, because it prefers to act as a base
Oh,
first instead of the electrophile, the bond between the H and oxygen pops onto the oxygen, giving it a negative charge, right?
I see. I see.
And then that H right there is going to be this H right here
Okay.
on this starred carbon right there, right? So acid-base reactions, the R group of the organometallic will not attach onto the reactant or the molecule.
I see. I see. Okay.
Uh-huh. But if it was a carbonyl or a haloalkane, it would attach there. Okay. Last one.
And I drew the cyclopentane, and
Mm-hmm.
attached to it is just carboxylic acid.
Yep, you got it.
Okay.
Nice. Okay. Yeah. What have you learned about so far in Bios class 128B?
Today's lecture,
Uh-huh.
we learned some alcohol mix.
Mm, some alcohol, like more nomenclature, or did you learn about like any
Not nomenclature. It's let's see, lecture two. He just talked about pKa and how it affects like
mm,
alcohols when you have more bulky like substituents, it increases the pKa.
right, the
Yeah,
acidity uh
yeah,
of
and
different
then
alcohols and pKa.
yeah, and then they got to conversion of alkyl halides.
Mm-hmm.
So they add like a strong acid in water to add a halogen on
Mm-hmm.
top where alcohol used to be.
Mm-hmm.
Uh, and then he talked about sulfonates,
Oh, sulfonate, like the good living group.
yeah, good leaving groups,
Mm-hmm.
and how you have to do like two steps to add to change an alcohol to an I think
So
it's secondaries, right? Secondary OHs.
secondary sulfonate to convert a bad living group into a good living group
The secondary
sulfonate.
alcohols, and then you change it to a sulfonate, and then
Uh-huh.
add the like a halogen salt.
Halogen salt. Yeah, yeah, I see.
Yeah,
Mm-hmm.
and then a reaction with thionyl chloride, S,
SOCO2.
yeah, with pyridine.
Uh-huh.
And he drew the whole entire mech, and it's like
Oh,
three side products.
oh yeah, it's a pretty complicated mech. Like the migration steps and like the weird
Yeah,
arrows. It's pretty complicated. That SLCO2 mech.
and then he touched a little bit on like which reaction does S and two, which one does S and one.
Right, like the primary, secondary, tertiary
Yeah,
alcohol. Yeah, I see, I
got it.
see. That's good. That's good.
Yeah, that's all we covered in 50 minutes.
Dang, that's a lot. That's a lot.
Yeah, that's a lot.
hmm Dang. Okay, so next office hours, I'll like probably like reinforce those because
Okay, yeah,
and make sure like we get it.
gotcha.
And for
Okay.
Elysia, we'll do more alkene stuff.
Yay, okay.
Yeah. Would you want more like reactions, nomenclature, acid-base stuff, or NMR, or synthesis,
Uh,
mechanism?
I mean, when you were explaining the NMR, that was actually really helpful.
hmm
And Helix was emphasizing that he's gonna have it at least like once on all of the exams. So,
yeah.
like that's something I can always improve on, and as
hmm
well as the alkenes react the mechanisms.
Right. Like the arrow pushing mechanisms for the thing like what kind of did today for the
Yeah,
isomerization
we
reaction.
also I also covered electrophilic hydration of alkenes, so like
Uh,
H2SO4 with water or H plus in water, um,
mhm.
and then hydrohalogenation.
Have you learned about the terms Markovnikov, anti-Markovnikov?
Yeah, I'm still kind of new to it, but I know it's like um, kind of the concept that we applied a little bit where it adds to the least substituted side of the asymmetric
Mhm.
alkene. So that kind of makes sense. Probably just more practice though.
Right. Yeah. Yeah. So it's basically what we just talked about already today. Like how we want the carbocation to be at the most substituted position. That's why we attack using the less subcarbon. That's the Markovnikov addition. Some
Mm,
reactions would go against that, which is the anti-Markovnikov
okay.
addition. All right. So it's just a fancy term of what we just talked about today.
Um,
Yeah.
okay, okay.
That's the regio selectivity of it. Regio meaning the region, like where the molecule attaches to, like the more subside or the less subside. Regio selectivity. Markovnikov, more subside. Anti-Markovnikov, less subside. Right. Later on, if you haven't already, you can learn about the stereo selectivity, like the spatial arrangement of the reactions. Like there's syn addition and anti-addition. Like
Oh, yeah, yeah, yeah. Ed
yeah,
over that.
hmm like that's good. That's good. Did you read it over yourself before Helix taught it?
Yeah.
That's good. That's good. We could go over that too. Let's go over that, like regioselectivity, stereoselectivity reaction of
Okay.
reactions, because those will, like probably be tested as a conceptual question because Helix asks conceptual questions, explanation questions, acid base, nomenclature, predicted product, mechanism, and synthesis. So the
Oh,
conceptual questions would probably be like, what is the regioselectivity of this reaction? Select the following reaction that has a syn addition in the mechanism, something like
okay, yeah. I'll have to have to work on
that.
that.
Yeah, don't worry because I have like the previous exams for previous quarters. I'll send it to you. Send it to you for
Yay.
you to
Okay.
review. Uh-huh. Yeah, that's good. Okay. Okay. Yes. Wiley, and could you also send me your notes and practice to Discord so then I could like check what Rio goes over as well?
Wait, what do you mean practice? Like
Or
you
if
don't
you
have any like practice. It's just textbook problems.
oh
But
yeah, okay. Just send me the notes then. The notes
the
would be
notes,
great.
okay, I'll send you right
Yeah.
now.
Okay. That sounds good.
Yeah. All right.
Okay. Good night, guys. Thanks
Thank
for
you.
coming.
Bye.
Bye.